Okay, since you know this already, tell me what kind of systems does Huckel approximation apply to? Planar and what kind of bonding? Pi bonding, right? Huckel approximation is all about pi bonding. If you go into sigma bonding, then you got a problem. Why? Because Huckel approximation sets the overlap integral to be 0, okay, which sounds a rather strange thing to say, isn't it? Because if there is no overlap, then at least in the valence bond concept there is no bond, right? Why are we justified in using a value of 0 for the overlap integral? Because we are restricting ourselves to pi bonds, right? Pi interaction is weak, isn't it? Okay. The internuclear distance has already been set by the sigma bond, you can think. It is a side on overlap, okay, which is weak fortunately, because I had a pi interaction with a cow few months ago right in front of chemistry kiosk. Fortunately, pi interaction is weak, that is why I was not hurt, but Professor V.K. Singh had almost a sigma interaction. So he fell, he cut his forehead. We had to take him to the hospital, no joke. So that is the difference between pi and sigma interaction. Okay. So pi interaction is weak, so overlap integral can be set to 0 if you keep one eye closed. You do not have to shut the other, but keeping one eye a little bit closed, we can agree with Huckel that Sij equal to 0. Okay. But yes, sir. I am coming to that. It is valid for neighboring atoms also, yes. And the other thing that Huckel said is that, he said that Hij is also equal to 0. So of course then that is a valid question, that then what are we talking about? But then there is a, you know that joke that somebody was asked to testify, some hen was stolen, and this witness was asked how big is the hen? He said this big, and then the judge of course blew his top. He said, how can you have a hen that is this big? He said, no, it is this big, I have not brought out the other hand yet. So Huckel is now going to bring out the other hand, right? Says Hij equal to 0 and sets us off completely, and then he says unless I and j are adjacent. Okay. So it is important to understand what is the physical meaning of this assumption. What he is saying is that pi interaction, you can say, you can consider that the interaction is only between adjacent atoms first of all. Secondly, since it is pi interaction, overlap is not that much. Okay. So as you will see, it works, but if you try to use this in sigma interaction, then you are completely lost. So what an approximation that holds in some system need not necessarily hold in another system. This is very important to understand. Science is all about, at least to start with, making intelligent guesses, but the guess has to be intelligent. Approximation cannot be such that it is completely bizarre. Okay? Fine. So first thing that happens is that normalization becomes very easy. So how will I write the molecular orbital wave function? Psi I equal to sum over j Aij phi j, and let me multiply this by a normalization constant Ni. Okay. What is the normalization condition? That integral psi I star d tau is equal to 1. So that is Ni square integral, okay, sum over j Aij square, let me put phi j also, phi j square d tau equal to 1. So what I will do is, let me write it in as two terms. Ni square multiplied by, first let me say sum over j aj square. There are two cases, right, where I equal to j and I not equal to j. Okay. So, first say aj square integral phi j d tau. Right. It will be a summation on j, right? Why not? That is right. Okay, evaluate this, see what you get. Evaluate this sum, see what you get. It should be sum over j a I j square integral phi j d tau. No? Sum over j a I j square, then integral phi j d tau, isn't it? Now evaluate, see what you get. What do you get? What is the value of n that you get if you evaluate this? The second one, of course, will be sum over jk aij ajk integral phi k d tau. Right. So, you work this out, you get Ni equal to 1 over square root of sigma j aij square. So, normalization constant becomes very easy. Okay. Yes, sir. Work it out, write the two terms. Which one? Which one? This? Break it up into two sums. Break it up into two terms. One in which you are going to get phi j, another one in which you are going to get phi k, where k is not equal to j. Work it out. Okay. The second thing that happens is, what is HII, what is HIJ? Tell me. What is HII? Huh. So, phi I integrated over all space. So, it means it does not stand for interaction between adjacent atoms or any such thing, right? So, you call this alpha, and this value is set to 0. That might sound as a rather drastic thing to do, isn't it? Why is alpha set to 0? Alpha will have some value, that is not a problem, but it is set to 0 because tell me this, will alpha be different for different carbon? Think of benzene. For the 6 carbon atoms, will alpha have different value or will it have the same value? So, how will it contribute to the energy of the system? It will just give it an offset, right? So, all I am saying is that whatever that value has gone to, that is because of the atoms themselves. Even in absence of bonding interaction, that value of energy is there. So, if I set that to 0, then what will happen is that anything that goes above or below that is going to be because of bonding purely. That is why alpha is set to 0. More often than not, it is written in terms of alpha, okay, if you want to get the absolute energy, but then many times it is set to 0. So, are you all clear why alpha can be set to 0? It is just the offset. Alpha arises out of the atoms themselves, not because of bonding or anti-bonding interaction. What is Hij? Hij stands for interatomic interactions, right? that is set, that is called beta. So, the moment I call it beta, what is it that I am assuming? When is Hij not equal to 0? When they are adjacent to each other. So, if I set the value of that to beta, irrespective of what is I, what is j, that means what I am saying is that the unit interaction is the same everywhere, isn't it? Right? So, this is often set to 1. So, in terms, so like see h by 2 pi is often set to 1 in many cases, right? You write in terms of, you just write square root of s into s plus 1 or square root of L into L plus 1. What is the angular momentum? You say square root of L into L plus 1, right? You do not worry about that h cross term, because you write it in terms of that, you call it the atomic unit, right? So, here also you are doing the same thing. You write it in terms of beta. Beta would have some value. Does anybody know the value of beta? But you have to say which unit it is also. 18 point something joule or calorie or kilojoule or what? So, first of all, it is set to 1. Another thing that is very important to understand is that, is beta positive or negative? It is a negative quantity, please do not forget that. Why is it negative? Because, so once again, it is a matter of convention. In thermodynamics, what is the convention that we follow? What is the modern convention? Anything that flows into the system is positive, anything that flows out of the system is negative, right? If you want to be a little more dramatic, you say anything that enriches the system is positive, anything that impoverishes the system is negative, right? So, it is the same thing. Energy is going out, stability means energy is going out. So, system is impoverished, that is why it is negative. So, it is an inherently negative quantity. Okay. So, if you set that to, if you write like this, then in terms of alpha and beta, what does the secular determinant become? This is the secular determinant for a 2 electron system, for a 2 atom system rather. What is H11? Alpha. Alpha minus E, right? And this is beta minus nothing. S12 is 0, do not forget. So, this is beta, this is minus, and this is alpha minus E. So, if I set alpha to be equal to 0 and beta to be equal to 1, what will the determinant be? This is what? Alpha minus E, right? And alpha is set to 0. So, what does it become? Minus E. Then what was the next one? Beta. Beta is set to 1. What do you write then? 1. What about this? This is also beta. 1. What does this become? Minus E. Now you have a very simple equation. What is it? E square equal to 1. So, E is plus minus 1, right? Plus minus 1 means plus minus beta. Which one is bonding, which is anti-bonding? Is plus bonding or is minus bonding? Plus is bonding because you are writing it in terms of beta, do not forget. Beta is negative, very good. Okay. Now, without working out all this, can you tell me what will be the secular determinant of naphthalene? There are 10 p orbitals. What will the secular determinant look like? It will be an extension of this, right? So, 2 p orbitals, this is what you get. 10 p orbitals, what will it be? So, what will the determinant look like? You will have E in the diagonal, right? And adjacent to E, you are going to have these ones. What was that? Other terms? Other terms will be 0. So, this is what it is. For naphthalene, this is what it is. Now, you put in alpha and beta and satisfy yourselves what it will look like. This is what it will look like in terms of alpha and beta. Okay? Simple determinant, you can solve it. Yes, but then if I set this in the endsem, then I have to set only this question, because you have to solve an equation where you have e to the power 10, right. So, what we want to do is, now we want to use symmetry. So far we had been talking about Huckel approximation, quantum chemistry only. Now we want to use symmetry. Okay. If we use symmetry, and we are going to see tomorrow how it works. Tomorrow when is the class? 5 o'clock, don't forget. Where is it? Room 350, seminar room, chemistry. So if I use symmetry, then what happens? So what we will do tomorrow is this: we are going to take those 10 p orbitals, right, and we will do what we are experts at. We are going to construct the reducible representation and we are going to break it down. In fact, to make our job a little easier, I request you to do it tonight. Okay. And when you do it, you see you are going to get this as the pencil: 2AU plus 3B1U plus 2B2G plus 3B3G. Okay. Then what we are going to do is this: we are going to combine them to form SALCs. SALCs will have the same symmetry, right. SALCs will also have the similar kind of symmetry. 2 of the SALCs, Psi1, Psi2 will have symmetry AU, 3 of them will have symmetry B1U, 2 will have symmetry B2G, 3 will have symmetry B3G. Okay. Then what we are going to do is this, that, so what happens in these SALCs? The symmetry adapted linear combinations, right. So when I consider Psi1 and Psi2, is there any need for me to consider Psi3, Psi4, Psi5, etc.? There isn't, right, because there are two things: one is symmetry, one is energy, another is symmetry. Here, since I have done symmetry classification, what I can do is I can work with Psi1, Psi2, then I can work with Psi3, Psi4, Psi5, then I can work with Psi5, Psi6, Psi7, and then I can work with the remaining 3 wave functions separately. There is no need for me to have a 10 by 10 determinant. Rather, what I need is a 2 by 2 determinant, a 3 by 3 determinant, a 2 by 2 determinant, a 3 by 3 determinant. So I am able to do what is called symmetry factorization of the determinant. Okay. Does this look more complicated or less complicated than the determinant that we just showed you earlier? I will not blame you if you say it looks more complicated. But at least there are more non-zero terms, it seems. But actually it is less complicated, because this determinant is block factorized. Hold on. I can work with the independent blocks. And what are these blocks? Psi1, Psi2, Psi1, Psi2, that is one block. Psi3, Psi4, Psi5, Psi3, Psi4, Psi5, that is another block. Psi6, Psi7, Psi6, Psi7, that is another block, and then the remaining three, another block. Yeah, Anu.
In the previous determinant, we had a couple of terms in the end.
Yeah.
That one is 1.
Yes.
The last one is the top of
This one. This one is 1.
So
We
we won't be able to block factorize.
will be able to block factorize, because Why is that equal to 1? Why is that equal to 1? What is this one due to? It is one atom on this side and this is one atom due to the other side. That is taken care of when you consider symmetry. We will do it in a little more detail tomorrow, wait until that, but we will be able to block factorize because the point is SLCs will have particular symmetries. Okay, we come back to this tomorrow. So, this is what we do and we make, as we will see, once we have small secular equations, it is possible for us to actually work out the energies first. We have not done that for benzene yet, right. So, what I will do is I will do it for naphthalene, I will ask you to work it out for benzene. Benzene is easier, do not even need such complications. And then once we know the energies, we will plug in the value of energy like what we said and we are going to find the coefficients. And then we will see some more complicating factor that will come in.